Have you ever been caught in a storm and thought, how is nature this wild? Today we're diving into weather so bizarre it feels like science fiction. Giant hail the size of grapefruits. Heat records that melt pavement. Fog that sits in valleys like a ghost. I can't promise we won't get soaked explaining it, but I can promise you're going to be amazed. We'll chase the insane physics behind each mystery and show you how ordinary conditions push the atmosphere to extremes. We're not just listing facts, we're revealing shocking secrets. How updrafts build monster hailstones. Why cities lock in heat and break records, and how dry lightning sparks megafires. You'll learn that some storms are literally recycling water to grow giants, and some heat waves are turbocharged by human choices. Ready to get soaked in science? Let's go. When you see a giant hailstone, don't think of it as a one-shot pellet. It's a snowball of circulation. Inside a supercell thunderstorm, there are violent updrafts that fling particles up into freezing zones repeatedly. Each trip through the storm adds a new icy layer like rings on a tree. The stronger the updraft, the longer a hailstone stays aloft and the bigger it grows. Updraft speed matters because it determines how long the hail can collect supercooled water. If the updraft can support a 2-pound lump of ice, the hailstone won't fall until it becomes too heavy. Meanwhile, the storm's internal winds and collisions sculpt the hail and trigger more layering. Think of it like a conveyor belt feeding liquid water to a growing ice pellet again and again. Temperature profiles inside the storm control whether layers are clear or opaque. Clear layers form when liquid water freezes slowly and squeeze out air. Opaque layers trap bubbles from rapid freezing. That layering reveals a history of each trip through different regions of the storm. Scientists can read those layers to infer how fierce the updrafts were and how many cycles the hailstone survived. So why do bigger storms produce giant hail? Because they have the powerful, sustained updrafts and abundant supercooled water needed for repeated growth. Combine that with a supportive wind shear environment, and you get the perfect hail factory. Heat waves feel unbeatable, but they're not random. They're the result of our changing atmosphere and local choices. Greenhouse gases trap more energy, shifting baseline temperatures upward. That means what used to be a once-in-a-century heat event now shows up more often. The atmosphere organizes into persistent patterns like ridges of high pressure that block storms and bake regions. When those ridges stall, heat piles up for days or weeks, turning normal summer warmth into record-smashing events. Add soil moisture loss, and the land starts to radiate more heat back into the air. Cities amplify these trends through the urban heat island effect. Asphalt concrete buildings. Nights stay warmer in cities, reducing relief and stressing humans' crops infrastructure. So a heat wave in a city can feel much more intense than one in a rural area. Combine greenhouse-driven warming, stagnant pressure patterns, drying soils, urban heating, and you get a recipe for recurring record heat. Understanding these links is crucial because it tells us what to target with adaptation and mitigation to reduce future harm. When it comes to cooling, not all shade is equal. An umbrella blocks sunlight, that's true, but a tree does something extra. It breathes. Through transpiration, trees release water vapor and move sap to cool their leaves. That evaporative cooling removes heat from the surrounding air, the way sweating cools our skin. Shade from an umbrella reduces direct solar radiation, but doesn't lower the ambient temperature the way transpiring vegetation can. Trees also create layered microclimates, cooler air near the ground, intercepted wind patterns, reduced thermal radiation at night. The result is living cooling that persists even after the sun moves. Tree canopies filter heat throughout the day and reduce the urban heat island effect at neighborhood scales. A street lined with trees can be several degrees cooler than one lined with buildings and umbrellas. So when you choose landscaping or urban design, trees give long-term benefits umbrellas simply can't match. That doesn't mean umbrellas are useless. They provide immediate shade and personal relief. But if you want sustained community-scale cooling, vegetation is the real MVP. Planting trees is like installing air conditioners powered by nature. Large-scale patterns like La Niña can shift storm tracks away for multiple seasons, producing a natural tendency toward dryness. When these patterns persist, short dry spells stack into multi-year deficits. So, soil moisture acts like a memory for the land. Dry soils heat faster and release less moisture to the air, which suppresses cloud formation and reduces rainfall, a feedback loop that prolongs drought. Essentially, the drier the ground, the harder it is to get rain back. Human water use compounds the problem. Over-extraction of groundwater, reservoir mismanagement, irrigation demands. When nature denies supply and humans keep consuming, the drought deepens and recovery becomes harder. Combine persistent climate patterns, soil-atmosphere feedbacks, and heavy human demand, and you get long-running droughts. Recognizing these interacting drivers points to solutions: smarter water management, conservation, and understanding of climate variability so communities can build resilience. Valley fog has a simple but beautiful origin. Cold air sinking into low spots getting trapped. At night, slopes radiate heat away cooler. Denser air slides down into valleys. Cold air can't rise past warmer layers above, so it pools and sets the stage for fog. Temperature inversions are the key. Warmer layer above cooler valley air preventing vertical mixing. Trapped moist air reaches saturation, condenses into tiny droplets, creating a sea of fog over river bends, fog-filling basins. Local humidity, calm winds. If it's still ground, is moist. Droplets form. Easily, fog can persist through the morning until sun mixes the layers, or wind mixes the layers. Inversions can be surprisingly stable, especially late fall, winter. So, valley fog is really a matter of geography and nighttime cooling aligning. Monsoons are massive seasonal breaths of the planet, driven by temperature contrast between land-sea. In summer, land heats faster than the ocean. Warm air over land rises, creating a low-pressure zone that pulls moist ocean air inland. That onshore flow fuels intense, organized rainfall. It's not just wind. The seasonal reversal of pressure patterns shifts the storm systems and positions the rain belt over continents for months. The timing and strength depend on how quickly land and sea temperatures diverge and on larger-scale ocean patterns. Local geography plays a huge role too. Mountains force moist air upward, cooling it and triggering heavy orographic precipitation. Coastal plains may get the weaker onset, while upland areas see the worst of the downpours. The result is a system that can sustain prolonged, torrential rainfall when everything lines up. Understanding monsoons means seeing them as predictable seasonal engines rather than random storms. With better prediction and planning, societies can harness the water while minimizing flood and landslide risks. Dry lightning sounds like an oxymoron, but it's a real and dangerous phenomenon. It happens when thunderstorms have high cloud bases and precipitation that evaporates before reaching the ground. The lightning still strikes, but the rain doesn't make it to douse sparks. High-based storms form when the lower atmosphere is very dry, so raindrops fall through layers where evaporation saps them away. The lightning originates high and travels to the ground, igniting dry vegetation that isn't getting the benefit of accompanying rain. This combination makes dry lightning a major wildfire starter. You can have abundant lightning activity and no moisture to suppress ignition. Fire managers dread these setups because multiple ignitions can start across broad areas simultaneously. Predicting dry lightning requires looking at storm base heights and humidity profiles, tools meteorologists use to warn fire-prone regions. When you hear thunder but see no rain, that's, a red flag for wildfire risk. Why does the same cyclone look different on different maps? The answer is partly science and partly convention. Storms are tropical cyclones, but regional naming systems and classification thresholds vary. Hurricanes, typhoons. Cyclones, same mechanics, different labels. All these storms share the same engine, rotating low pressure, warm ocean heat organized convection. What changes is the Ocean Basin Regional Meteorological Agency local naming traditions. Once winds cross a fixed threshold, agencies assign a name from pre-approved lists. Naming helps with communication and public awareness. Thresholds for naming retirement of names categories like Super Typhoon versus Major Hurricane. That can be confusing when tracking storms across basins. So while the physics is consistent globally, the labels are a patchwork of history and policy. Understanding that distinction helps you interpret different forecasts and appreciate how societies prepare for these powerful storms. Rainforests are nature's recycling plants for water. Sunlight heats the canopy and surface, driving massive evaporation and transpiration. That moisture feeds convection above the forest, forming clouds that rain back down, a self-sustaining loop. Heat-driven convection is the primary engine. Warm, moist air rises, cools, and condenses into towering cumulonimbus clouds that produce intense, often daily showers. The rainforest literally engineers its own rainfall through this cycle. The dense vegetation and complex canopy structure recycle water locally and also generate regional atmospheric patterns that draw moisture from far away. Deforestation interrupts this loop by reducing evapotranspiration and changing surface temperatures, which can diminish rainfall. Protecting forests preserves the very processes that make them wet and biodiverse. That muggy, sticky feeling before a storm is your body sensing the atmosphere charging up. As humidity climbs, the air holds more moisture. Sweat can no longer evaporate efficiently, leaving you feeling clammy. But that humidity is also the fuel for storms. Instability. Moisture. When surface humidity rises, sea breeze frontal boundary surface heating. Rapid convection can be triggered. The more moisture in the air, latent heat is released when it condenses, amplifying updrafts. Dew point. Specific humidity are better predictors of storm potential than temperature alone. We just tore through 10 weather mysteries and turned chaotic-looking events into understandable processes. From hailstones growing in storm elevators to monsoon winds driven by land-sea temperature battles, each mystery has a physical explanation that connects to everyday life. That knowledge isn't just cool trivia. It helps us prepare, adapt, and sometimes even predict what's coming. If you learned something wild, like how dry lightning can light whole forests or how trees act like living air conditioners, drop a comment with the fact that blew your mind. Share this with a friend who thinks weather is just random and challenge them to a weather trivia bet. If you enjoyed the ride, smash that like button and subscribe. Stay curious.